The Restore project aims to develop a groundbreaking technical solution to store excess heat in summer for the winter season, when energy demand is higher. One key technology in the innovative Restore concept is Thermochemical Energy Storage. As part of the project, researchers from the Technical University of Vienna substantially advanced this technology by extensive material examination and by manufacturing thermochemical energy storage pilot plants.
Thermochemical energy storage is the process to store energy in chemical reactions, and this can be achieved over long periods of time without losses. And in comparison to other technologies, the energy density is significantly higher and the temperature levels can be adjusted to the requirements.
The working principle of thermochemical energy storage is based on the reversibility of chemical reactions. In charging mode, heat is added to an oil solid suspension reactor to split the thermochemical material into a charged solid and a gaseous compound. Uncharged material is transported from a vessel, passing a preheater to the reactor, where the chemical reaction takes place due to heating. After recooling and separating the solid material from the oil, this charged material is stored. The gaseous compound, in this case water, is condensed and stored in a water container. In discharging mode, the chemical reaction is reversed by recombining the solid material with water using the same reactor, and heat is released and extracted via an internal heat exchanger.
The chemical and thermophysical properties of numerous TCS materials were thoroughly analyzed. The most optimal candidates were selected with energy densities up to 1.11 gigajoules per cubic meter suspension. This is roughly 3 to 4 times the energy density of water. Various types of mineral, silicon and vegetable oils, individually and in combination with each other or additives, were evaluated. The optimal combinations for reaction were determined. Thus, cycle stability in up to 30 charging-discharging cycles for 5 chemical systems was proven in a lab-scale batch reactor.
Stable continuous operation with heat charging and discharging cycles has been successfully proven with copper sulfate and potassium carbonate in our 1 kilowatt continuous glass reactor. With the insights gained with the glass reactor, the operation conditions of oil and particles have been optimized for best conversion.
Building upon these foundational advancements, TU Wien has developed 2 large-scale reactors capable of operating at pressures up to 10 bars and temperatures up to 200 degrees Celsius, paving the way for larger-scale applications. The design and development of these pilot reactors went through an intensive engineering process to ensure optimal performance in terms of mass and heat transfer, meeting the requirements of practical implementation.
Leveraging the insights from various investigations, including the small-scale demonstrators, a 5 kilowatt thermal TCS pilot plant is manufactured. It is an intermediate scale-up step for the Restore 30 kilowatt thermal pilot plant. The TCS materials and the reactor design are evaluated under various operating conditions.
The design of larger-scale pilot plants were optimized through numerical simulations and experimental studies. Innovative sparger designs and impeller designs were tested and investigated to find the optimum conditions in heat and mass flow within the preheater and the reactor, as well as good quality mixing. After being tested individually, the 30 kilowatt prototype will be connected soon to the ORC prototype to test the Restore concept.